Welcome back. There's an underlying standard in relational databases that makes them suitable for many use cases, but also limits their scalability. Some information systems require a database to take extraordinary measures to protect data integrity across replicas. Use cases might be bank accounts or class registration. For example, when you're preparing your schedule as a graduating senior, you would like to know if a course is filled so you could try a different course at the time of registration. On the other hand, there are other applications that need high availability, and they deal with large volumes of data. Because of competition, these applications require low latency. The ability to handle changing workloads is scalability, and relational databases can scale up to a limit, but they're challenged with scaling out because of their two-phase commit. The enormous concurrent user counts on the global internet makes this a necessity for a lot of different use cases, having the ability to scale out. Popular web applications are evolving over time, and that's a problem also with static data models. Just as an example, Twitter changed its format a couple of years ago, and among other things, it now has much larger data content, twice as much as before. So to handle this, they create replicas, which are copies of the database in different locations to handle that load and latency. The question is, how do we maintain consistency between the replicas? Do we require that a change in one replica is immediately reflected in another? That's something you would want with student registration. Or is it okay if a change in one replica eventually shows up in all the other replicas? For example, Facebook. It's not that critical that people on the West Coast don't see a change immediately when you make it here in Baltimore. NoSQL databases are designed for scaling out over multiple low-cost servers. They have distributed data algorithms that are designed for a server that may fail and other servers in the cluster taking up that workload. NoSQL databases are highly distributed, and they can easily add and remove servers as needed. So, databases that support ACID, such as relational databases, have an important role in information technology, especially supporting immediate consistency use cases. There are other use cases where performance, especially scalability and robustness, where you're able to handle a server going down without really breaking a sweat, becomes more important in those use cases than immediate consistency. So you have to look at the use case you're analyzing to decide what type of database to use. If you need immediate consistency, then relational databases are still your best choice. Use cases include information systems in social media also, mobile devices, and the Internet of Things. Such use cases have to process massive amounts of data quickly. So we need new tools. That's not to replace the old tools, but to supplement them. A NoSQL database is a tool that makes a different trade-off in the consistency scalability balance. A new principle, not acid, but base, explains this trade-off. So let's look at a example. Let's say we had two servers and they had exact copies of the registration database, the university database. And at registration time, you could go to either server and you could put in your class requests. So what would happen if this did not have immediate consistency? Immediate consistency is a change in one replica is immediately reflected in the other replica. Well, what would happen is you might, you don't want to register for a semester and think you got the classes you need, only to find out later that the server was not immediately updated with changes from the other server, and you didn't get one of the classes you needed for graduating. So we need a way to ensure that a change in one server is database is immediately reflected in all the replicas. So they do that with what's known as a two-phase commit. So things start off where the coordinator, where the original update was made, sends out a broadcast, I've got a transaction, tell me when you're ready to do the transaction. And then all the other replicas will come back and say, okay, ready, 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 ready. I'm not ready. So then if that happens, then it's got to start over, because by the time, by a certain amount of time has elapsed, you don't know if the first server that got back to you is still ready to go. So you keep doing this until you get everybody ready to go in that time window. And then you say commit after you've got that part done, which may take a while. Then you say commit. Then you wait for them all to come back. Okay, complete. But what happens if one of them comes back and says, I couldn't complete it, someone locked the record in the meantime? Well, then you've got to roll back and start over again. And you can see that becomes problematic as you add 50, 100 servers, and you've got to do this across the world. You make a change one place, it's got to be immediately reflected. Makes it difficult to do. So that's why they say relational databases can scale up. In other words, more powerful hardware, but obviously you run into limits faster scaling up. If you can relax that two-phase commit requirement, then you can scale out. And that becomes much easier to scale, but you lose that immediate consistency. Now, immediate consistency is not needed for a use case like Facebook. Doesn't really matter if your homepage on Facebook in California doesn't reflect a change you just made to your page on a server in Baltimore. Instead of two-phase commit, they use other update approaches like message gossip or quorum two-phase commits and other approaches. But the idea is they're relaxing immediate consistency to gain horizontal or scale out capabilities. So here's the ACID properties of the relational model. Atomicity, either all the actions are carried out or none are. And if you'll remember 2 weeks ago when we were going over transactions, I did an example of a transaction in Transact SQL for Microsoft, and we saw how that works. We have a bundle of updates or inserts, and either all of them go through or none of them. Consistency, if each transaction is consistent and the database is initially consistent, then it is left consistent across all replicas. And then isolation, you don't step on other people's work, and then persistence, the work you do is retained. So when no updates occur for a long period of time in a NoSQL database, eventually all the updates will propagate through the system and all the nodes will be consistent. But at any given time, as long as it's active, that's not going to be the case. Replicas will not be consistent. So you have to look at your use case and decide if that's acceptable or not. So for a given accepted update and a given node, eventually the update reaches the other replicas or nodes in your database network. Now, NoSQL databases use a different set of guidelines than ACID that we just looked at in the last slide. The guidelines they use are basically available, soft state, eventually consistent. Soft state, that means copies of the data item may be inconsistent, and basically available means that you're going to have a system that's available. That's very important in these type of applications, more important than immediate consistency. So let's look at NoSQL in light of this discussion. It's a new category of database management system. It does not use SQL as its query language. It does not use joins, which require this strong consistency and fixed schemas. NoSQL databases are more flexible. They're not a replacement for relational databases in large transaction systems like banking or sales. They are viable for large systems that can tolerate a temporary inconsistency that eventually works itself out. So this is a guide. You can't have everything, so pick two. And that's the trade-offs you're going to be making. With MongoDB, we have consistency and partition tolerance. With other databases that are more relational, we have consistency and availability. With others, we have availability and partition tolerance. Partition tolerance occurs when networking fails between nodes so that it creates separate partitions. This means that the server will still be available and can still eventually make the data consistent. So the network breaks into multiple parts. Your replicas are in each one of the parts. They can continue working and taking in updates. And when the network is repaired, they can propagate those out. There's four main categories of NoSQL or not only SQL databases. The simplest is the key value pair. The value part is unstructured, and you could consider it to be a CLOB, which is a large text object. So it's limited to query by the key value only. So you have the key, and then you have all the rest of the data as one lump. The essence of a key value database is one attribute per key. You can't really structure the data, but you could use some complex schemes to structure your key, but it becomes problematic and it's not really intuitive. Document databases really were the answer to this problem, and we'll get into them in just a moment. A column database actually is a SQL database, but it's also categorized as a NoSQL database. Normally, data is stored by row, in other words, row by row on disk, but here it is a file for each column, or in other words, column by column storage on disk. And it's optimized for reading and writing columns rather than rows. And then we have a document database, and the document database extends the key value databases by adding structure to that clob or that big lump of data, which means you can query on non-key fields. So you can add structure to your data with named fields that are similar to JSON or a Python dictionary. And then lastly, we have a graph database, and it focuses on relationships between data. It has vertices, which are entities, and edges, which are relationships. Graph databases often have an underlying storage that can be SQL-based. Graph databases are a return to the network databases of the pre-relational era in the 70s. The big difference is that with graph and SQL databases, the relations are always fixed in the graph databases, whereas the relations are based on data joins in the table, so they're more flexible and can be adapted with foreign key attributes being added in to the where clause. So let's look at one of the more popular NoSQL databases, and that is the Mongo database. So Mongo has three main parts. MongoD, which is a Mongo database server instant. Mongo, which is an interactive shell. And this, like the SQLite command shell, is a fully functional JavaScript environment for use with MongoDB. Of course, in the case of the SQLite, it's not JavaScript we're using, but SQL that we're using. And then MongoS is a sharding program, which is middleware that routes queries between a client and any of the backend MongoDB instances. There's here's some of the characteristics of a MongoDB, which are, it's one, a document-oriented database. It's based on JSON. So many of you have probably used JSON. If you haven't, it's very similar in concept to a Python dictionary. It's a set of key value pairs, and the value part can be also key value pairs, or it can be lists or arrays of things, or it can be just final atomic values. It's organized into collections of documents, and it has, again, this intuitive JavaScript query language for retrieving, updating, and inserting documents. It supports both an aggregation framework, where you do aggregation functions like sum, average, min, max, those kind of things, and also MapReduce. MapReduce was the original way you would do those type of aggregation functions, but Mongo has since added in an aggregation framework that is more intuitive, I think, to the relational database world. And that's where the bulk of the database administrators and designers and programmers were coming from when this started out. We can compare the organization of MongoDB with relational databases. So at the highest level, both are dealing with databases. In the relational model, the next level down is a table within the database. The equivalent in Mongo is a collection in the database. Then a table will have rows, and a collection will have documents. A row will have columns, and a document will have fields. You can also input indexes in both of them. You can partition, and the term in MongoDB is shard, and you can join, and in MongoDB you can have embedded documents. And again, this is how the hierarchy looks. Databases are composed of collections which have documents in them, and the documents have key value pairs, which are fields. So document-oriented means it's using a JSON structure. And again, most of you should have had Python in your introductory classes here at UMBC. And if you have not used JSON, it is in essence a dictionary structure you're used to with Python. And again, MapReduce was the original approach to handling complex transactions and data analytics. It's still available, but they also have a much more intuitive way of doing it with the aggregation framework. So here's some of the basic operators. We use a database to make it the current database. And this is similar to Microsoft and MySQL, for example. To access a collection, we use the DB handle and then the collection name. So if there's a collection in our database that we just used, the name 461, db.cmsc 461. Some of the commands we can issue, we can find instances in a collection, db.computerscience.find, and then we can say db.computerscience.find, and we can put some search filters in. And likewise, we can do db.computerscience461.find1, and that'll bring up one record. And we can insert data in with the same DB handle, CMSC 461 collection name, and then the insert command. And we insert data as dictionaries. And we'll do a demo of this in just a minute, but we start up our database server and we give a path to our database using the DB path parameter. I just named mine MongoDB_data. And then after that's working, then we'll start a MongoDB client, which goes by the name mongo.exe, and then connect to our database and use collections. We can use a database, and then we can get the collection names, and then within a particular collection, we can find out how many records are in there with a count. So let's take a look at how we start this up. I'll change my share. So as was indicated in the slides, I'm in the path where I put my MongoDB executables, which for me is C MongoDB bin. Then I start up MongoD, which is the service that runs in the background that does the database management system work for us. It's the database engine. I give it a path to my data, and my data is in a folder called MongoDB data. So I hit enter, and now it's waiting for my client to start up, or some client to start up and connect to it. So let me switch to another window, and I'm going to then go Mongo like that. And this connects, and now that I'm connected to the engine, and it connects by going to the port that is by default listened to. I could have named other ports, but by default, it's going to listen on port 27017. So I just left it as the default port to listen on for the server, and the default port to speak to by the client. And we can see I've got a couple of databases. Show DBs is a command that is going to show the databases we have in our particular folder. So I'm going to use CMSC 461. Now I've got that, and I'm going to go DB. Well, I'm going to go show collections. I'll show you what before I actually get one. So these are the collections equivalent to relational tables that we have. And of course, this is from our bank database. Let me extend this a little bit. Now let's go to a particular collection and let's find the records in it. So this is kind of like a select star in relational, and you can see there's the records. Key value pairs, okay? The ID and then the value for the ID. The field named city, and then the value for city, field named name, and then the value for the name. Let's contrast that with what we've been doing with SQLite 3. So I'll go over here, start up SQLite 3 with BankDB, and so let's switch over. Okay, let's switch over to SQLite 3. So now we're in SQLite 3, and we'll look at the branch, and you can see we have the same type of information: name, the city it's in. We could have added a primary key that is unique, and the database keeps track of it for us. We didn't do that. In Mongo, it automatically adds that. So same data though, but instead of a document format, we keep it in a tabular format. Reason originally was the design team of COD and the others felt that a tabular format was more intuitive for people to use. So let's switch back over here. And here's, again, that same data for branch in MongoDB. It's there, it's just that instead of in columns, it's in key value pairs. Okay, so let's go back to our lecture. There we go. So Tengen was the company that made up MongoDB. And its original, and this was like 10, 11 years ago, its original vision was to leverage the work that Oracle, IBM, and others Microsoft have done over the last 40 years with relational databases. They didn't feel a need to discard decades of proven database maturity and all the algorithms that were used in the relational database systems. Instead, they augmented them where they needed to handle this new idea of eventual consistency and scale out. So it combines key relational database capabilities with the work that the internet pioneers had done to address these requirements of modern applications. Again, its query language is JavaScript, so very expressive. You can add indexes and things like that into the database. And we've gone over strong and eventual consistency. And of course, Mongo designed it so that it is able to integrate in with existing information technology infrastructure. So, just like MySQL, MongoDB allows users to mix and match multiple storage engines within a single deployment. So that gives you a great deal of flexibility in how you can handle various use cases that you need to resolve. So traditionally, multiple database technologies would be needed and be needed to manage to meet that type of need with a complex custom integration code to move data between the technologies and ensure consistent, secure access. With MongoDB, they have this flexible storage architecture, and the database automatically manages the movement of data between storage engine technologies using replication. I mean, that's their strong suit anyway. And ever since MongoDB version 3.4, MongoDB ships with 4 supported storage engines. And the one they're currently using as the default was actually developed by the user community. And Mongo, or Tengen, thought it was a good approach, and they integrated it in. So the default is this new approach, well, not new now, but at the time, new approach called the Wired Tiger storage engine. And it gives you very granular concurrency control, very effective compression, very good overall performance, and extremely good storage efficiency. So it's good for a very broad range of applications. This is part of the Community Edition, which is the free version. You also have the option of an encrypted storage engine. And obviously this is good for protecting highly sensitive data without the performance or management overhead of separate file system encryption. This isn't free. This comes with the paid versions of MongoDB. Likewise, the in-memory storage engine, extremely high performance, coupled with real-time analytics. And that's one of the ways that MongoDB markets themselves is you can do real-time big data analytics. Although their big data is not nearly the big data of Hadoop or Spark, but it is, fairly substantial. So it will meet very demanding, latency-sensitive, big data type applications, although it doesn't scale to the extent that Hadoop and Spark do. Hadoop, of course, is a batch-oriented system, not very fast. So that's where Mongo could really come in with some competitive marketing. Spark is very fast, so it's 100 times faster than Hadoop, and it scales to the level of Hadoop. So different world. So watch for Mongo to start dropping that marketing angle because of Spark. The last database engine is the MMAP version 1. So this is the original storage engine that was used in pre-3.4, version 3.4 MongoDB releases. That was the original one. That was the one you got. And then with 3.4, they added this Wired Tiger. And then, of course, you got the other ones. If you're a paying customer, you got the other ones. So again, in Mongo, data is stored as documents, which are JSON structures, a JSON representation that you can have a lot of flexibility in defining the data types and data structures that you need. Mongo documents contain one or more fields. Each field contains a value of a specific type, including other dictionaries, arrays, binary data, subdocuments, embedded documents, and so on. Okay, and now we have some group time for you to work on the group project. Thank you.